increasing and rapid deterioration and degradation of water quality is one of the most challenging issues that the 21st century is facing. It can be ascribed to a variety of factors such as population growth, the effects of climate change on the hydrologic cycle, and increasing pollution. This also significantly affects quality of fresh water sourced for human consumption. Globally, extensive research has been performed to address such an urgent issue, and new technologies and materials have been developed to treat drinking water and wastewater in order to remove potential contaminants, including the emerging ones. However, the cost and challenge associated with water treatment and the increasing awareness of environmental and human health risks call for continuous improvement and innovation. Nanotechnology has significantly contributed to remarkable industrial and societal changes over recent decades. Among the wide variety of fields of application of nanotechnology, considerable efforts have been devoted to exploiting the potential of engineering nanomaterials, in general for environmental remediation and for an effective water treatment, in order to remove traces of contaminants at very low concentrations and to guarantee both low-impacting treated wastewater discharge and drinking water safety. The advantages of the use of engineering nanomaterials relies on those unique properties associated with at least one nanoscale dimension, which are bound to a peculiar chemical affinity, surface charge density, and electron transfer ability. These characteristics confer outstanding catalytic, adsorptive, optical, quantum, electrical, and antimicrobial properties for environmental applications. Despite such promising expectations, environmental and human risk assessment associated with the use of engineering nanomaterials is a matter of debate, and the application of these systems for water treatment is still seen as an emerging field. They have been slowly applied in Europe, mostly because of the emerging societal worries on nanotechnology and the current lack of regulatory and proper legislative supports. In fact, the particularly desirable characteristics of engineering nanomaterials, which make them suitable for water treatment, can negatively rebound of the safety of application of such materials. The current debate relies on the balance difficult to handle between known benefits of nanotreatment and costs related to potential risks associated to the use of engineering nanomaterials in natural matrices, including drinking water, mainly due to their mobility, transformation, and potential eco and human toxicity. For this reason, guidelines to implement the use of engineering nanomaterials for water treatment are strongly recommended. In 2007, Dahl and co-authors proposed the 6 Greener Nanoscience and Nanotechnology Design Principle, with the aim to provide useful tools for a sustainable design of engineering nanomaterials and minimize undesirable implications. He took inspiration from the 12 principles of green chemistry, which more and more drive the synthesis of new molecules and materials. Among these principles, the first one, design of safer nanomaterials, is the most challenging, but also that which, once realized, would allow to overcome the issues and concerns related to the implementation of nanotechnology for water treatment. To translate this principle into practice, Dahl recommends determining the biological impacts of nanoparticle size, surface area, surface functionality, and utilizing this knowledge to design effective, safer materials and to avoid the incorporation of toxic elements in nanoparticle compositions. Hence, we need to understand how to design safer nanomaterials for water treatments. Here are some guidelines deriving from our research experience in the field. A first winning point relies on the correct selection of safe sources for the synthesis of final nanosolutions. For this reason, the choice of biopolymers as starting materials is becoming an important target. In particular, polysaccharides, bearing several functional groups, provide interesting opportunities both for their easy processability to obtain nanoparticles and for their intrinsic nature, as for cellulose, whose hierarchical structure can be cleaved up to attain nanofibers and nanocrystals. Biopolymers can be considered also as valuable supports for fixing inorganic nanoparticles and prevent their mobility. In some cases, also enhancing the final performances in terms of adsorption and disinfection efficiency. Moreover, by considering that they can be extracted and efficiently purified from biomass, also derived from agricultural waste, this approach allows to enter a virtuous chain of recycling and reuse to produce upscaled products, following the guidelines of circular economy. Last but not least, final disposal of bio-based materials is much less impactful than other commercial solutions. A second valuable strategy to overcome the toxicology and the legislative issues related to the use of engineered nanomaterials for water treatment consists into the simple concept of moving from nano-sized materials to nanostructured devices, transferring the advantages of nanotechnology to macro-dimensional systems. Following this approach, nanomaterials are cross-linked to provide nanoporous networks with high surface areas, becoming the building blocks of a final solution. Lastly, but not less important, the ecodesign as a key instrument for obtaining safe materials. By assessing the potential human and environmental hazards associated with a specific application of selected engineering nanomaterials for water treatment and sanitation, environmental risks can be significantly reduced if their assessment is performed since the beginning of a product design. The ecodesign concept, already developed in other material sectors, here will be applied to add environmental safety testing, named as ecotoxicity, to identify those critical properties of engineered nanomaterials and nanoparticles that could harm biota and design out them without compromising nanomaterials' properties and efficacy. Nowadays, the nanosafety assessment is performed on those materials that are already on the market, while here we propose to adopt an ecodesign strategy since the beginning of the product design, along with testing their performances and efficacy. Ecotoxicity data can be used as a guide to design safer engineered nanomaterials and nanoparticles for environmental application as water treatment and sanitation, thus allowing the development of new eco-labeling, which stands for a more holistic ecological safety. The development and backbone of a proposed holistic eco-design strategy of engineered nanomaterials embeds bio-based raw material sources, a green synthesis following the principle of green nanoscience, a high decontamination efficiency, and sustainable application processes hand in hand with nanosafety assessment for humans and receiving natural ecosystems.